So here's your silicon wafer, and I already prepared the surface, like I did the HMDS treatment because that is done in INRF, not here. So HMDS treatment, and then I cleaned it today before using it and kept it for dehydration. So to make sure that there is no moisture, there's nothing on top of it. This is a bare silicon wafer, doesn't have any oxide or nitride, but it always has some native oxide, like a few nanometers or so. So that's why it's always a good idea to clean it and dehydrate it, okay? So now after the dehydration, we'll just wait because it was done at 120 degrees C. We'll just wait for the wafer to cool down, and then we'll spin coat it. So this machine is the spin coater. If you remember, you had a picture of this on your slides as well. Before using any machine, I need to log in, because then for as long as if I use it for 10 minutes or a few hours, they'll charge me on my account. So I need to, so the machine only works when I'm logged in. So as you can come and see now, you have the display is now on, because now here is the vacuum line. We need to create vacuum in order to hold the vapor on top of it. So here, this is the vacuum chuck, and this is where it will create vacuum, and you will be able to see the reading and how much vacuum is there. And so that's where you place your vapor. And now turn on the vacuum line, and then press vacuum. So, and then make sure that it's there. And right now I'm just checking at what RPM it's already set. So initial is for 10 seconds is 500 RPM. And after 10 seconds it should be 3000, because that's what I want for my process. Now, how do you decide what will be what's the RPM or what's the speed for your process? Is so that's set at 3000. So there are SU8 data processing sheets that are provided by the manufacturer, or you can just download them from Google. And there is a curve, there's like a graph that tells you for a certain type of SU8, which is like a certain viscosity of SU8, what is the height, and that corresponds to a certain speed of spin coating. So I'll show you the data sheets. They look like this. And so if you can see, it has like SU8 2075, 2050. These are different names for SU8s, and they are just based on different viscosities. And then you see, if you want to make, say, 80 micron height, you need to spin coat it at 1000 RPM. So that's very simple. You have everything on here. What you need to do is just take your SU8 out. I'm using SU8 2015. As you can see, this is 2002. This is so thin, but this one is a little more viscous. And thicker SU8s, you have 2150. That's really viscous. If you open the bottle and tilt it like this, it will take about 3 to 4 minutes for it to even come out. And those SU8s are even more difficult to handle, but if you need more than 100 micron height, then that's what you need to use. Okay. So this is approximately 5 ml SU8. If you're not comfortable pouring it directly from the bottle, use a dropper or pipette or something. In fact, that's how it should be done. Now, no matter, even if you pour a little extra SU8, you will still get the same thickness, and the extra SU8 will be get deposited onto the walls. Okay, all set, and we now run it.
Why do you put that little piece on?
Oh, that's just because the SU8 splashes out sometimes, just for the cleaning thing. You can see it, right? That's all right. Okay, so after spin coating it, the next step is to soft bake it. And soft baking is done either using a hot plate, or you can also use ovens. It is done at two temperatures, 65 and 95. And again, for how long you need to do your soft bake is there on the sheets. So that's like, it'll tell you like you have tables like this, 25 to 40 micron, need to do at 65 for about 3 minutes, 95 for 6 minutes, or something like that. So I have one hot plate for the 65, and then that oven is preset to 95, so I'll use that for the second half of the soft bake. Okay, this is done. You need to make sure that this is uniform, and that during the process you try to keep your wafer as flat as possible. So your hot plates are perfectly flat. Oven needs to be flat, like all these shelves in the oven. If it is tilted, then you'll have your SU8 flowing. And you don't really see it, but even if it's like a few microns here and there, then it kind of changes the entire process. So just make sure. So we'll do this for about 3 minutes. That's the requirement of the process. And so we just need to wait for 3 minutes. So 3 minutes in this one, and then about 6 minutes in that oven. Okay.
Every time you have to do at 65 and then at 95?
Every time it's 65 and 95. I mean, and that depends on the photoresist. If you're doing it for, so whatever photoresist you're using, a positive Shipley photoresist or something, you have a different process, but they will give you the data sheets for that process. So this is for SU8. Okay. Wake up. We'll tape it. So if the wafer is covered with nitride, for example, or oxide, it looks like this.
Oh.
It looks so pink, and the reason is it's a thin layer of nitride, about 800 nanometers, so it changes the refractive index of the surface, so that's why it looks pink. But otherwise there's no color, but it's just because of the structure. So this is nitride coated wafer, and then you also get oxide coated wafers, depending on the on what kind of process you're using. And by the way, you see these two flat surfaces here, this one and this one. If you remember from the last microfabrication class, so these are called wafer flats, and this and this, when they are like at 90 degree to each other, this means this is a 100 oriented wafer. So that basically means if you break the wafer, it will always break in a straight line like this. It's a single crystal, and it will always break in the 100 direction. But if it is a 111 oriented wafer, the wafer flat is at an angle of 45. So I'll show you one 111 oriented wafer. I hope I have one. So this one, actually, I don't have an entire wafer. But you see there was this flat over here, and then this was at an angle of 45, and this was like, I didn't even check, it was kept in a box of 100, so I just fabricated on this wafer, and then when I tried breaking it after fabrication, see, it doesn't break where I want it to. I'd like it to break, you know, where I have given the space in my mask. So this one actually breaks, so this kind of, the structures became useless for me. So. Okay, I'll change it to the 95 oven. Okay, we need to wait for another 6 minutes. No, I didn't know because it could be 6 or 6.5. That it does. What's most important is when you're doing the UV exposure, you need to make sure that the time is perfect. Okay. I know maybe some of you have already done it, but if you want, you can practice breaking the wafer and see how it breaks in a straight line. You'd like to do it? Sure. Okay. Yeah, sure. I'm sorry about that.
That's okay.
Sorry?
Is it cheap?
No, it isn't. But we're using it for the practicum. Okay. Oh, that's the one.
So how do you
Okay. Now you have to always break it perpendicular to this, or parallel to this. So it's like perpendicular to this or this. So what you do is you just make. This is a diamond scriber, so it has a diamond tip. Very small diamond, but a diamond tip. And you just make a small scratch or a mark like this. It's very small, you don't really need to apply any force or anything. So you see there's this very small mark over here. And now what you do is you hold your wafer over here and here on both sides of that mark and put your fingers like this and just break it. It breaks like this. Okay? So try doing it. Now try to do it like perpendicular to this. And it doesn't take any effort. When you'll do it, you'll see it does break in a straight line all the time. Yeah, that's it. That's enough. It does, right? Okay, you guys should try it. So I'm just taking the wafer out from the post bake, from the soft bake, and I'll let it cool down for a couple of minutes. Okay. Okay, so I've just left the wafer for cooling down. The next step is exposure to the UV light. So why we've done this is to get rid of solvent. That's the soft bake step. So we want to make sure that the layer, the SU8 layer that we had, it was liquid, right? Now we want it to become solid. We want it to become glass-like. And why do we want that is because now the next step is to attach it to a mask and then do the UV exposure. So if there's any solvent or if it's not completely dried up, then it will damage your mask. So you need to make sure that it is completely hardened, and that's why we do the soft bake. So maybe you can now see if I do this now, that I don't leave a mark, like it's not, so it's like this. Okay, now I'll use a mask. So this is a mask. This one is a chrome mask. It is brown on one side and it looks like this from one side. This is fabricated using e-beam lithography, and it has like features that are down to 1 micron separation. This is used only when we are using kind of something very sophisticated. We are going down to 1 micron feature sizes, and this is only used using a mask aligner, which is not here in this room. It's in the other room, MA56. And what we do is we place the mask there and then keep the wafer down there, and then put them together and create a vacuum contact and then expose it to the UV light. Now for today's demonstration purpose, because that process will probably take long, I will just use a simple mask. This is the one where, you know, if you have 10 micron or bigger sizes, then you can use this kind of mask. These are much cheaper. That mask will cost you about like more than $1,000. This will cost you about 150, something like that. So for practicing many designs and you know, the starting thing, or for base layers, we use this kind of masks. So we'll use this. First we need to place it onto the wafer and clip it, and then there's a UV lamp there. That's not an aligner, not a mask aligner, it's simple UV lamp. So we'll go and expose the wafer to the UV light.
So if you were to design your own mask, would you
Oh,
set it
yes.
out to
Yeah.
create it, fabricate it?
Yes, so you need to design your masks in either AutoCAD or SolidWorks, and these are the only formats those people accept, and then they fabricate it.
But there's nothing you create like here in the house, right? For your own mask here. You always
Oh, no, we don't really do the mask fabrication here. I mean, it's possible, but it'll probably take really long, because using e-beam lithography, and one needs to be trained in e-beam lithography to that extent that it's kind of not feasible, so we get them fabricated. So I make sure that this line here is aligned with the line on my mask. So when I break it, it breaks between the designs. And you should not touch where you have your designs. So I'm making sure that I'm only touching at the corners or edges. Okay. And given SU8 is a negative photoresist, the areas that we want to have on our wafer are transparent. So the light will go through and will cross-link those areas, and the rest will be dissolved when we develop it. I now need this top. Okay, not this one, the other one. Okay, I'll just use my watch then. Okay, so I logged in again in the machine, and now I'm going to expose it to the UV light for about 30 seconds. That was for 30 seconds. So the next step is post-exposure bake. It's still too hot. Okay, the hot plate is still kind of, it shoots up every time it overheats. So I just want to make sure that it's done at the right temperature. So I'm just removing it from here for a few minutes because the hot plate is still at 70. I want it to come down to 65 because this is an important step, the post-exposure bake. Soft bake, still if the temperature instead of 65 you have 70 because you're just evaporating the solvent. But in this case you are actually cross-linking it because what the UV light has done is initiated the photoinitiators in SU8, and now they will act as a catalyst and do the cross-linking. That is done during the post-exposure bake, and that was a question also in the exam. So we don't do post-exposure bake for some photoresist, and especially positive photoresist, because see, in that case we are degrading that area which is exposed to the UV light. So we have some polymer and a certain area is degraded, and then we are washing that away. So we don't really need to cross-link anything. And this step is done for cross-linking. So it's only done mostly in case of epoxy-based negative photoresist. Okay, by the time it's cooling down, maybe I could go and show you the MA56 and tell you how it is done. Something that we did not do that here, but I can show you the machine. Okay, so the hot plate has reached approximately 65, so I just kept it, and now I need to do that for 3 minutes and then again for about 5 minutes at 95. And afterwards we'll develop it. So
this is a soft bake?
No, this is the post-exposure bake. Soft bake was the first one. This is the post-exposure bake. And once we are done with the entire process, if we want to do something else like etching or lift off or something else, if we want to take it forward, then we do the hard bake, and then we before the next step. Okay, this can get boring at times because you have to wait for 5 minutes, you can't do much. And also it's like you're not even allowed to bring any reading material here because ideally paper is not allowed inside clean room. So this is the only paper we are allowed to bring inside. And even this is not allowed if it's a higher class or like a better clean room. Even this is not allowed. Also, if you have a cold, you're not allowed inside. If you wear any makeup, you're not allowed because even makeup, or if you apply anything onto your face, it sheds particles. So, but here we are not that strict because it's just 1,000, or even like rooms outside are 10,000. And in case of, for example, in industrial processes, it's all automated. So you do not dispense the SU8, you don't pour it like that. There's an automated dispenser. And they always make sure that the ovens and hot plates are at the correct temperature. Also, the UV lamp is a very important thing. What happens is, so how do you calculate the, how long you need to expose it? These sheets will give you the exposure energy. it will just tell you something like whatever 150 millijoule per centimeter square. Now what you need to do is divide this energy by the intensity of the lamp, and that's what gives you time. So you can use any lamp. You can actually even use TLC lamp, but if it's too low intensity, you'll probably have to expose it for like 2 minutes or something like that. So, and what we do is we actually check the intensity, or the clean room staff, they check the intensity of these lamps every week or so, and there's a chart over there. They write down what is the intensity of the lamp, and that's how. So, and you also have, they sometimes give you an intensity meter if you want to be really accurate and you want to measure the intensity, because for the UV lamps the intensity goes down as the lamp ages, so you need to make sure that's the exact intensity of your lamp, or the entire process may go wrong. Another 30 seconds.
It just shows that you've done a good job.
Yeah.
Oh, really?
Because all these things were that good. Oh yeah.
That's what I would do.
How?
He
I
taped
put,
all your.
I put reading material on the outside.
Yeah, I know. Somebody can stand outside
Yeah,
and flip the pages for me. Yeah. Yeah, I can ask an undergrad to do it.
Come, you get to see the clean room.
I know, free training. So yeah, sometimes when for example, now this gets worse if you're making higher structures, like if it's a 200 micron thick structure, you need to do baking for like an hour. So in that case, I'll do it like before lunch. I leave my wafer inside and then come back and things like that.
So what if someone doesn't know it's in there? And they
Oh, you need to leave a note. You need to leave a note. If you cannot leave anything unattended, and if you do, then you need to leave a note with your phone number, and because if it goes wrong, like especially hot plates and ovens, because they're hot, and you need to make sure that nobody, there's no accident or something. In fact, no hot plates are allowed after 5 p.m.
So if you open this, it'll ruin it like completely, or?
No, I mean, because if you open it and close it within a minute, I mean like within half a minute, then it should be fine. But usually, because all the users who are here, they know that someone's wafer might be inside. Like they're all trained users, so they don't do it, like they don't leave it open for a long time. Okay, so I'll take the developer out meanwhile. Okay, so this is the SU8 developer, and again you buy it from the manufacturer, and you don't know the exact composition, but it's a chemical called GBL, gamma butyraldehyde or something, but it also may have something else that we're not. It comes with this brand name.
That's weird. Got a kick.
Well, and his wife did stop his training.
You don't have day drinking training? What?
So I pour some developer in here, and it should be kept inside the hood all the time. And all the wet processes must be done inside the hood. So I'll dip the entire wafer in it, and then again wait for like 5 minutes, and the undesired parts will get washed away. Yeah, after developing, nothing. That's the last step. You can go. Yeah, because we're not doing any further etching or anything. In fact, these structures that I'm making we'll make carbon out of it. So we'll just pyrolyze the entire wafer and convert this structure. So these are actually electrode designs. And now I'll use electrospinning and deposit fibers that connect those electrodes. and then those fibers are actually used as like for sensing purpose. So, so I need the entire structure to be conductive because the electrodes, right? So SU8 is not useful for me, but I can make carbon and then make it conductive. So I'm not going to do any further photolithography.
So what we're doing now is not going to waste, right?
It's not, sorry?
Not going to waste?
No, I'm not wasting. Like it's kind of, you know, these chemicals are too expensive. That bottle of SU8 is like $500. And everything is so expensive, and even the wafers and everything, and the effort. So why waste? Okay, so again, it'll cool down for like a minute or so. And if you can see, there are latent images, like, okay, can you see?
What am I looking at?
Okay, do you see some
Sorry.
patterns onto this?
Yeah.
Huh? Okay, they're not very clear yet because we've not developed them. They are latent images, and we should not tilt them too much.
Oh, I think I see.
I don't want to tilt them too much.
Okay.
Okay, so let's go and develop them, then you'll see it much more clearly. So we'll wait for like 5 minutes again and let it dissolve. And I hope it comes out well, because no matter how many times you do it, even if something small goes wrong, for example, the temperature of the hot plate, you know, if it shoots up or if it's too low, it might really destroy your structure. So every time you're never sure if you'll get it right.
So you just dip it in there and it means like...
Yes, we just, I mean, you can shake it a little bit once in a while,
Okay.
but you just dip it, that works too. Okay, so see, they're also doing it, but they're using a, oh no, that's not a problem. They're just using a different photoresist, and so they have a different developer for it. And that's a nitrogen gun, so once you develop the structures, then you clean it. Clean it using, for SU8 we use IPA, because the uncross-linked SU8 is soluble in, or it leaves a white precipitate in IPA. So if you see some white spots, then you know that's still not, it needs some more developing. It's not done yet. Okay, so it's coming out fine.
It's a waste after that whole solution becomes a waste.
Yeah, that SU8 is, so there's a bottle here that says used SU8, used SU8 developer. So we keep pouring in. So some, if there is kind of a rough process, people can use the used SU8 developer also. But it's kind of, yeah, it's a waste afterwards. Okay, so it's, do you see the patterns now?
Yeah.
Right, now they're much more clear. But it's not completely developed yet, because it should be done at least for 6 or 7 minutes for this thickness. So I'll dip it in for some more time. And then we wash it and dry it. And then I'll do the SEM later on to check if, because it looks fine now, but maybe my smaller features are, I don't know if they came out well or not, but then they're too small, they're like a few microns. So I need to do SEM to check if the separation is proper or not.
So you are currently working on this photolithography?
Yeah, so I'm working on carbon MEMS.
Okay.
And so we do photolithography and convert it into carbon MEMS. So we fabricate different kinds of electrodes basically for making sensors. Now they could be electrochemical sensors or just electrical sensors. So different people working in on different designs. Interdigitated electrodes, whatnot. Sorry. IP, I'll take that one.
Okay.
Oh, that's okay. If you're using it, fine. So that's IPA. And
Yeah. It'll be funny if I get a table from this. It's like, why? Get the second part of it, I'll start with it.
okay, I'll dry it with nitrogen. Hey, I'm sorry. Just 1 minute. Okay, there you go. So these are your patterns.
They're connected.
No, they're actually not connected. It looks like, so there are two 10 micron thin electrodes and they're like this. And then perpendicular to that, I electrospin a fiber. So that is what makes the connection. So in fact, when I'll do the SEM, I'll check if they're connected, then it's bad design. You know, it's kind of, it didn't come out well. But I want them to be separate, but of course you can see it through your naked eyes because it's like, they're very fine features. So that's what you fabricated. Okay?
And then you etch it.
Now you can do whatever you want to do. Now you can either etch it, or in my case, for electrospinning, what I do is I'll break it like how we broke. So break it, so kind of each chip will be used separately. I'll first break it and then electrospin on it and then pyrolyze it. So yeah. So that's pretty much it.